Ion dipole. The attraction between an ion and a polar solvent most important example is how ionic compounds are solvated by water. Go ahead and write that down. Look at some examples. All right, an ion dipole is the attraction between an ion and a polar solvent. Water is polar. Water is the polar solvent, and the ions come from ionic compounds. For example, sodium chloride. Salt dissolves in water. How's it doing that? Yeah. Okay. Here's how it does that. A cation is solvated by a polar covalent molecule when the polar covalent molecule, like water, points its partially negative end at it. So in solution, the polar covalent molecule is able to break apart the crystalline lattice of the ionic compound by pointing its partially negative ends right at the cations. Remember, opposites attract. This is a cation with a real positive charge. Here, if you have a polar covalent molecule, a region of that molecule has a partial negative charge. Opposite charges attract. Partial negative cation, they're going to interact. The opposite would be the other part of that, obviously, is how is the anion from the ionic compound going to be solvated? Well, for like sodium chloride, that would be a chloride. And what's going to happen is the partially positive hydrogen atoms are going to point their ends right at it, right? So polar molecules are able to solvate ionic compounds because a polar molecule has both a partially negative end and a partially positive end, and it can surround the cation one way and the anion another way, and that's how we do that. This interaction between a polar covalent molecule and an ion, a polar covalent molecule and an ion, these interactions are called ion dipole. Are they intermolecular forces? Yeah, but it's different, right? I mean, this is only in the aqueous phase or when it's dissolved. I think it's different than the typical, LDF dipole hydrogen bonding. How strong are these interactions? They can even be stronger than a hydrogen bond, right? They're pretty darn strong, right? Because the ions have an actual charge. So this is a big old Coulombic attraction. So these are strong, but I consider this to me, it's a different kind of intermolecular force. It's still between things, so it's intermolecular, but it's not quite the same. So that's an ion dipole. Fantastic. All right, yeah, nailed it. There's ion dipole. Much better picture than I could ever possibly draw.